Okay, and so basically what I'm going to talk about today is, well, I'm going to talk about networks. I don't have too much time. I have 2 hours. So I will talk about different aspects of networks, of different types of tools that people can use in order to deal with networked systems. And I'm going to focus more in detail on one particular aspect, which is community detection, some sort of form of clustering for graphs and networks. But just before we start, I just wanted to give you a broader perspective of why personally I find networks interesting. So I've been interested in something called complex systems for quite a few years since I started my PhD. And usually it's not that easy to define what complex systems are. And the best way to explain what it is to go through an example. And a very good example would be looking at birds flocking together. So you are confronted to a system where you have birds flying together. Each bird is a single entity. They are interacting with each other. And even if there is no leader, you will observe the formation of beautiful patterns in the sky. And that's a good example because, first of all, it's an example that everybody knows. Everybody's been walking around on the beach in the countryside looking at birds flying together. It's an example where you see that even if there is no central entity, you can have the emergence of patterns just due to the interactions between each of the birds. Well, it's something beautiful, and I think that science should be beautiful, so it's just beautiful to watch. And you see that these patterns emerge not only in space, but also in time. They are moving around. So, very good. So now the thing is that, when people are interested in complex systems, well, what they're interested in is how patterns are emerging. So how order is emerging from chaos. How is it that we observe nice patterns around? How is it that we have very nice birds flying together and not flying completely randomly in a very chaotic way? And just a short slide from the 19th century. So I don't know if any of you have heard of the Maxwell demon at some point, no? So that's where you see that I have a physics background. I studied physics originally, even if I'm now in math. Well, in the 19th century, people didn't try to understand why order emerges. They tried to understand why disorder emerges. And that was at the era of thermodynamics. And the second law of thermodynamics tells you that the disorder of a system is going to increase in time. And at the time, people tried to understand why you would have this second law of thermodynamics, why you would expect that disorder is emerging in time. The thing is that was what people were interested in the 19th, but in the 20th, people changed viewpoint and they said, okay, we understand why, we understand the concept of entropy, we understand why disorder has to emerge due to physical laws, but yet around us, we don't observe a chaotic world. What we observe are very nice patterns all around us. And these patterns can be, well, they can be spatial patterns, but they can also be temporal patterns. And those would be like fireflies whose activity is synchronized in time. Very good. So, and basically, as a scientist, I'm interested in this emergence of patterns. Why do I observe patterns? And how can I spot, how can I extract these patterns, usually in very noisy systems? Now, if you want to deal with a complex system, a complex that is composed of many elements that are interacting with each other, you can use all sorts of tools in order to represent and to analyze the system. So you can use tools from dynamical systems, for instance. You can use all sorts of tools from data mining and optimization. The thing that personally I've been developing some expertise in using networks as a way to represent systems composed of elements. And why would networks be a good model for such system? Well, of course, it's just a model, it's just an abstraction, but it's an abstraction that emphasizes the importance of the connections. So it means that you might put aside certain aspects of the system, certain aspects of the data, but what you try to emphasize is the impact that the connectivities of the system might have on how the system behaves. And the good thing is that networks provide you a language that you can use to describe extremely different systems. You can think of social networks, you can think of biological networks, you can think of information networks. All of these systems can be modeled as networks. So you will have nodes and connections between them. even if the meaning of the nodes and the meaning of the connections are completely different. So it means that this system and this one here, they're completely different. The meaning of the nodes and the meaning of the edges are extremely different, but yet I can use exactly the same tools in order to represent them on the board, but also in order to try to extract something useful from the myriad of connectivities. Good. So, but as I said, and it really something that's quite important to keep in mind is that networks are just an abstraction. So it means that very often, when you adopt a network in order to represent a system, you will discard some information. So for instance, that's this example from the Königsberg bridges of Euler. Well, it's a classical example from graph theory. Well, that was an example where Euler went to a city, was interested in how different regions of the cities would be connected by bridges. Well, if you're just interested in connectivity, you don't need to care about where the buildings are, so you can discard this information. You don't need to care about the geographical layout. All you need to do is to represent the different regions and the connectivities between them. And of course, because if you're only interested in connectivity, you don't need this extra information. But you should always keep in mind that sometimes when you adopt a network perspective, you might have thrown away some extra information. But after you did that, after you've been representing a network, or a system by a network, then, well, as I said, very different systems can be represented by the same tool. So here, it's an example from the internet, where you would have routers connected with each other by physical connections. Here, it's a nice example. I think it's the first sociogram. So it's something that it dates from the 1920s, 1930s, by a psychologist called Renaud, and he invented something called a sociogram, where, and it was on the front page of the New York Times at the time. And so what is that? So he went to a school, he looked at kids, and these would be the boys, those would be the girls, and he looked at who was playing with whom, and tada, of course, you would observe that there is a segregation, and when you're 6 or 7 years old, well, the boys play with each other, the girls play with each other, but there are just a few connections between the two groups. So here, that would be an example from, I think it's a brain network. So we'd have different regions of the brain that are connected with each other if they have some functional relations, if they tend to be activated at the same time. And here, that would be an example of a food web, where you would have like species and connections between the species if they are feeding on each other. And so as you see, well, again, very different systems, very different meaning for the nodes and edges, and yet you can use the same tools to represent them and analyze them. Very good. So now, how does this relate to data? Well, the thing is that, well, nowadays, well, I guess I'm the Turing Institute, so I shouldn't say that too much, but we are flooded with data. Data is coming at a pace that is too fast to deal with. And the thing is that very often, interesting data come in the form of networked data. You will have connections between different types of data. And that's certainly the case for social media in general, where you would have that, well, social networks have become quite important for the last 20 years. It means that many systems will tend to have, will have a very strong network structure, where you will have different elements that are connected with each other through different types of connections, usually. So personally, how I see the kind of research that I do, how I try to summarize it, well, usually I deal with data. So I will have I'll deal with real world data. And from this data, what I try to do is to try to answer two different types of questions that are somehow feeding each other. On the one hand, what I try to do is I try to extract some information from the data that I have, either using existing tools or developing new tools. So I have data, I try to get some insight and some understanding about how the data is organized. And on the other hand, I'm also interested in some theoretical challenges, because I'm interested in trying to build models that can reproduce the data as I observe them. And the thing is that these two aspects are somehow related, because you will have that the data, the knowledge that you have about the data is going to be fed into the models. So it's going to help you to produce some new models and usually some new theoretical challenges. And at the same time, better models can lead you to develop better tools, better methods, better algorithms in order to extract information from the data. So really you have the data, the tools, and the models, and well, I think I do my best to try to focus on these three aspects together. So okay, so now what is a network? So maybe I'm just going to ask because I don't know. I think that I have a very broad audience in front of me. So has anyone ever had a course of graph theory one day in his life? Okay, it's a minority. Has any one of you ever had to deal with data that had networks in them and using some methods or tools for network analysis? Okay, it's a minority as well. So very good. So that's good because we start from the start. So what is a network? So as I said, usually a network would be it's a system where you would it's a model where you would have nodes that are connected with each other. And the thing is that networks can be usually encoded in different ways. And one classical way to encode a network would be by the use of matrices. So again, in terms of math, does anyone feel comfortable with matrices? Yes, it's okay? Okay, good. So you would have matrices, and the typical matrix would be what's called the adjacency matrix. And what is it? So you will have a 0 if you don't have a connection. You will have a 1 if you have a connection. So it's a binary representation. So of course here I have an example where the graph is undirected. There is no direction to the edges. So that would be fitting, for instance, for Facebook, where you have like bilateral relations between people. But if you were interested in Twitter, we would have directed interactions, and then the network would be directed. And if the network is directed, the matrix here wouldn't be symmetric anymore. Here it's symmetric, but it needs not to be the case. Yes. And also, if you want to, you can also make the model more rich by including some weights on the edges. Let's say that you have some information about the strength of a social interaction. In that case, you would have a weight on the edges, and in this case, you wouldn't have ones, but you would have the weight of the interaction in the matrix. Okay, so this is one way to represent that graph, and these two ones are exactly equivalent. Yes, from here I can build this, and the other way around. Now the thing is that why do I present this adjacency matrix? Because as you'll see just a bit later, it's a very convenient way to think about networks from a mathematical perspective. Because when you have a matrix, you can use all of the very nice and beautiful tools of linear algebra in order to try to extract some information from the matrix. Yes?
Is that necessary to have this symmetric matrix? Because in like Facebook, it's kind of symmetric, but I can imagine a relationship like a leader, like a supervisor and PhD student.
Then that would be something directed, yes?
And that still fall into this domain.
Exactly, and in that case, the matrix wouldn't be symmetric anymore, but it would be asymmetric. So you would just have, let's say that instead of having a 1 and a 1, you would have a 1 here, and a 0 here, just to show that there is an asymmetry in the relation. Yes. So now the thing that you'll see later is very convenient from a mathematical perspective, and also in order to develop tools, but you pay a price in practice because let's think about Facebook. Facebook has about 1 billion users, and it doesn't seem to be very, very smart to try to encode a graph of 1 billion users with a matrix, keeping in mind that this matrix would be made mostly of zeros. Because on Facebook, so 1 billion users, on average, people have around 300-400 friends. So it means that on each line of that matrix, you would have 300 or 400 entries that are different of 0, and the rest would be 0. So it's not really the most convenient way to store the information. So it means that in practice, you almost never store a graph as a matrix. What you will do instead is storing it as a list of connections. So you'd say there is the link 1, 5, 5, 2, 5, 3, 3, 4, and so forth. But still, it's important to keep in mind that you can think of them as matrices because that can be used afterwards. Okay, so now, so people have been interested in networks for many, many years, but really, like, I think that for the last 20 years, with the access of large databases of network systems, people have tried to extract some commonalities, some general properties that you observe in very different systems. And one of the most influential observations that people made in the 90s was the fact that if you look at what's called the degree distributions, what's the degree distribution? So the degree of a node is its number of connections, yes? And then you can, so if you have a large graph, you have a large number of nodes, you have a large number of numbers that are the degrees, and you can just do an histogram of that. So you can simply measure this distribution. That's going to tell you what is the probability that if I take a link at a node at random, it will have a certain number of links. Yes. So here to the right, people have many links. Here to the left, this one has 0 link. And the thing is that if things, in classical views of graphs, people tend to assume that graphs would have a shape like this one. So it means that you would expect that the distribution of the number of links would be roughly distributed around the average, either like a Gaussian or something like that. And so it means that there would be like a good notion of what's the characteristic number of connections of nodes. Now the thing is that when people looked empirically, what they observed was something extremely different. So people would say that this would be fitted by a power law. People would say it's fitted by another kind of distribution. But the most important is that the kind of distribution that people observed were extremely different from this bell shape. And what it induces is that in many empirical networks, what you will have is a strong heterogeneity, some links with an extremely large degree, some links that play the role of hubs with a very, very large number of connections, and the vast majority of the nodes that just have a very, very small number of connections. And that's something that people have been observing in, maybe I have, no, I didn't put it. It's something that people have been observing in very different systems. So if you look at Facebook, if you look at the web would be a very good example. If you consider the web, well, obviously you will have certain pages that receive a large number of hyperlinks, yes, but you will have that the vast majority of pages just receive a few links, either from their parents or their mother or whatever. So it means that so you have a very strong inequality in the system, and this strong inequality is important because it will affect the way the system is organized, but also it can affect how to search for information in the system. Because if you look, for instance, and we'll do it a bit later for clusters, groups of nodes that are well connected, well, if you don't take this into account, you might have a very different answer than if you take it into account. So that's some information that needs to be kept in mind. So, no, that's not really important. So, so there are some observations that people made. So now, and I'll come back to other observations after. I just wanted to start and give a few slides about the notion of models of networks. So when people look at networks usually, so they have access to some empirical data, and they make some observations. So they observe that the degree has some properties, other things have some properties. But then at some point you want to answer the question, is it expected or not? Is it something that is remarkable, or is it something that I would have expected just because that's the way it is? And in order to answer this question, typically what people do is to build models of networks. So what they try to do is they try to build stochastic models, random models of networks that have certain properties in order to show whether or not some observations are unexpected or if they are simply what you would expect in a random model, basically. And how do people build models of networks? There are many ways to do so, and typically they are divided in two families. So the first family is really has a statistical nature. So what people would do is to consider, for instance, so the most basic model is what's called the Erdős-Rényi model. So Erdős, you probably heard of him, I guess some of you. Rényi was also a Hungarian scientist. He developed something called the Rényi entropy. And we go back to entropy as from the start of the introduction. But okay, so the Erdős-Rényi model, it's from the 1950s, and it's a very simple model. Where I assume that you have n nodes. What you will do, you will consider all pairs of nodes And with a certain probability, you will make a connection between them. Otherwise, you don't make a connection. So it's an extremely simple model. So each edge is an independent Bernoulli process with the same probability to happen, so a certain parameter p. And what you do, so you have n nodes. You have n times n minus 1 divided by 2 pairs of nodes. And for each of these pairs, well, you throw a coin. With a certain probability, you will have a link. Otherwise, you don't have a link. And so that's an extremely simple, it's a very naive, very simple model. But it has very beautiful properties because you can calculate analytically almost all of its properties and make predictions about how it's going to behave. And for instance, what you can, and so it's important to keep in mind that this model corresponds to an ensemble of graphs. So it means that you have parameters, but because it's a stochastic, it's a random model. Well, of course, from one realization to the other, you will have different properties, right? Because from one throw of dice, you will have one graph, another graph, another graph, another graph. So all of these graphs are possible, but they might appear with different probabilities. Yes, and in principle, so the thing that the Erdős-Rényi network, well, almost every simple graph can be realized. So it could be possible that with a certain set of parameters, you will have an empty graph, so just nodes and no connection. That would be possible, of course. Or you could have a full graph, the set of nodes, and everybody is connected to everyone. But these two extreme configurations will happen with different probabilities. Yes. So, and the thing is that for this ensemble of graphs, this random ensemble, we can calculate all sorts of properties. For instance, you can calculate what would be the degree distribution, the one I talked about before. So the probability that a node has a certain degree. And then it's kind of easy to show that it's going to be something looking like a binomial distribution that looks very much like a Poisson distribution in certain limits. And the thing is that that's where you see that, for instance, this model, well, it's a model that doesn't do well as compared to empirical data, because you would have that. So that would be an example from the internet. So some real life, real world data of a degree distribution. This would be for the collaboration between scientists. We would have people who worked with each other. Here you would have protein interactions. You would have proteins, and there's a connection between them if they tend to interact in certain reactions. Well, in these three scenarios, you have the red curve and you have the dark curve. And what is that one? That would be the corresponding degree distribution for the Erdős-Rényi model with the same number of nodes and same number of edges. And you observe here that this black one and this red one are quite different from each other. So from here you can draw two conclusions. The first one is that it's very likely that the empirical system is not generated as the Erdős-Rényi model. So it means that what you could expect is that because the red and the dark are very different from each other, you could expect that actually the internet, science collaborations, and protein interactions are not generated completely by chance. Well, it seems to make sense, I suppose. But then it also means that if you want to build some more faithful model of reality, well, you need to improve on that model. And that different ways to improve it, and typically the ways to improve it is to continue to think in terms of ensembles of graphs. So again, this probabilistic point of view, but by putting some constraints on the graphs. So what does it mean? So if you think about the Erdős-Rényi model, we looked at all of the possible graphs built where each edge was independent. Well, it's possible to try to put some constraints by, for instance, allowing only certain types of graphs. Among all of the possible graphs, you restrict, and you only look at certain of them that satisfy some constraints. And you look on this sub-ensemble from the initial ensemble. And so now, instead of looking at the statistical properties of the whole number of graphs that are possible, you will restrict on some that satisfy certain constraints that are either are motivated for physical or biological reasons, or due to observations that you've made in the past. And one of the constraints that can be done, for instance, would be to impose a certain degree sequence. So what does it mean here? So it means, let's assume you observe a graph, you calculate the degree of each node, and then what you want to ask is the question, okay, so now I would like to build a random graph such that I will keep exactly the same degree for each of the nodes. So of course, if you look at the degree distribution for the original graph and for the model, it's going to be the same by definition, yes, because you keep the degree exactly the same for each node. But then you can compare other properties. You can look at all sorts of other things and check what would be the difference between the original data and the ones associated to this random model. And the way to do typically is, is to keep the degree sequence conserved. And how would you do that in practice? Well, for instance, let's assume we have a small graph here with 4 nodes. We know that the first one is 3 edges, the second one is 2, the other one 2, the other one 1. Well, what we do is we see that each of these extremities is the end of a connection. What we do is we completely reshuffle everything, and we connect 2 ends randomly with each other. So it means that, for instance, one realization would lead to something like that, where this one with degree 3, 2 to 1 have been reconnected, such as to preserve this constraint completely randomly. But of course, it could also happen that due to this randomness, you would have a self loop appearing. You could have that this node is connected to himself, or you could also have that some pairs of nodes are connected by multiple edges. That's something it's possible. It's a possibility by chance. And so this ensemble of graphs that are generated, so I just have 3 realizations, but I could have many more, obviously. This ensemble of graphs is something called the configuration model. And the configuration model, so it's really an ensemble of random graphs preserving the degree sequence that you observe in empirical data. And usually that would be a model that many people use in order to confront what they observe to a model, because this model at least has this strong heterogeneity associated to it. If the original data is heterogeneous, the model is going to be heterogeneous too. Yes. So of course there is one small caveat, is this possibility for having self loops and multiple edges, and that's something that might not make sense for the system that you are considering. But luckily enough, if your graph is sufficiently large, it can be shown that under some generic properties that the number of self loops and the number of multiple edges is vanishingly small as compared to the total number of edges. So it means that in practice, if you have a large network, it's relatively safe to use such a procedure. And in practice, what would the people do? They would generate the graph according to this procedure, look for self loops and multiple edges, and remove them. So by doing that, you might decrease just a bit the total number of edges, but in principle, this decrease should be marginal, because for large systems, the number of loops and the number of multiple edges is not large. Very good. So that would be for the configuration model. And just something that we'll need to that we'll be using just in the second hour of the talk is for this model, for this configuration model. Well, you can estimate what would be on average the number of connections that you have between 2 nodes. And so what you would have as an answer is this thing here. So what would that mean? So Ki would be the degree of node I, Kj the degree of node j, and 2m is just a notation for the total number of edges. And so here this quantity in this model means the expected number of links you would have between 2 nodes, take I and j. So when you think about it, why would that be something like that? Well, it should be proportional to the number of connections of node I, because the more connections as node I, the larger would be the number of links that are connected to him. And it should also be proportional to the number of connections of node j for the very same reason. So it should be proportional to the product of the 2. And actually, it's relatively easy to show that, well, the system is large enough that would be exactly equal to this quantity here. And simply because if you have a node with a large degree, another one with a large degree, it's very likely that they will be connected with each other. Just because each of them has so many edges that one bit of this one will connect to another bit and make a connection between the two nodes. And you'll see we'll be using this property here when we'll be doing some clustering. Very good. So that was for the first type of model. And the first type of model was really very statistical. We have a certain random rule, and then we look at all of the configurations that can arise from that rule. Now, the thing is that there are also other types of models that people have been interested in that are more mechanistic ones. So these mechanistic models, they are a bit less well-defined from a statistical perspective, but what they try to emphasize is the mechanisms by which the network has been evolving in time. And a very, very influential model is a model for growing networks, where you try to understand how the system has grown from a small network to a very large one. And how would these types of model evolve? Well, you would start from an initial configuration, and then you try to imagine that a new node arrives in, and it connects to previously existing nodes with certain probabilities. And typically, something that people would do would be to say that a node connects with a higher chance to high-degree nodes than to low-degree nodes. And this very simple mechanism is something that has been existing for a long time. So if you go back in history, so I don't know if anyone has heard of Polya. So Polya is a very important statistician from 1940s, I guess. Well, the Polya-Earn model is something called, it's a multiplicative stochastic process that has the very, very same ingredients incorporated into it. It was not about networks, but it was about multiplication. And why do I say multiplication? Because I just told you that you have a higher chance to connect to a high degree node, but then it means that at a later stage you have a higher degree. And so you will have an even higher probability to be connected. And the more the time advances, the less equal should the system is. Because if you have a slight advantage, it's going to be multiplied in the future, basically. And that model of Polya, so it was then developed for networks specifically, and it was known as, like Merton has been looking at it, but one of the nice ones is from Herbert Simon. Herbert Simon, Nobel Prize in Economics. He looked at this model, especially for networks in the 60s, and he developed a model where basically the system was growing in time with this notion of rich gets richer. The richer you are, the richer you're going to be in the future. And here, rich in terms of connections, not in terms of money. And the thing is that in the 90s, Barabasi and Albert developed a very, very similar model than these ones, and they called it preferential attachment. Again, you attach preferentially to nodes that have a higher degree. And so to close this, and so the thing is that so there are these two different types of models, probabilistic ones, mechanistic ones, and for these mechanistic models, what you gain is you can try to understand how certain rules can lead to certain types of organizations. And also the thing is that for these kinds of models, you can also solve things analytically extremely easily. So it means that for all sorts of variations of these models, you can calculate many properties by hand. And that's good because then you don't need, you can then compare what you observe from the predictions of your model, for instance. Very good. So far I only talked about one aspect, that was the degree distribution, the distribution of the degrees present in the system. But of course, it's a very naive way to summarize a graph. Like a graph, as we said, so in principle, it's encoded by a n time n matrix. And here, I summarized it simply by looking at the degree of each node. And so I was just interested in how the distribution of these degrees was looking like. Now, the thing is that there are many, many metrics that people have been developing in the last decades in order to characterize either the graph as a whole or single nodes. And for instance, one type of measure that people have been interested in is trying to measure the local cohesion of a graph. So is the graph that you have very random or very cohesive? And for that, the classical way to do would be to look at the density of triangles that are present in the graph, because triangles are a measure of cohesion. So typically for social networks, for instance, well, if you have a very cohesive group, it's associated to the fact that if I have two friends, they're also friends with each other. My group is a coherent group. And in sociology, these configurations would be understood to be stable configurations. So when you have a triangle, that's something stable because, well, there's no reason for this current configuration to change. An example of unstable configuration would be if you take a network with signs, positive or negative signs, and you have friends and enemies. Well, if I have two friends and these two friends are enemies with each other, well, that wouldn't be a stable configuration because I personally would be put in a stressful situation. Every time I talk to person A, I cannot mention person B, and the other way around, right? Everybody's gone through these kind of ugly situations. And so, for instance, in sociology, that would be a kind of pattern that would be unstable and would need to evolve in time. And there are different ways to do so. Either A and B become friends with each other, that's the ideal situation, or I take side and I decide to go with A and I become an enemy of B, for instance. Or I become enemy with everyone because they just piss me off. That would be a third way. But so it means that, so there are all of these notions, for instance, especially in social networks, about stable configurations. And usually the stable configurations are associated to local cohesion and the presence of local triangles. And so in order to measure that in a graph, well, there are measures called the clustering coefficient that are going to be measuring the density of triangles that you find in a graph. Another question that people are very much interested in is the notion of centrality. How do you say that a node is central or not? And for centrality, well, I could talk of centrality for 2 hours. So there are many, many ways in which you can define centrality. The most simple one would be to say that a node is central is if it has many connections. That would be the degree. But that's not a very interesting one. There are other ways to do so. And for instance, you could say, no, a node is important if it tends to be on the path connecting people. Yes? And that would be, well, if you think of a road network, that would be a good point where to put a tax office, such as the goods are taxed between the two different countries, for instance. Yes? And these nodes that are between people, they are extremely important, again, for instance, in social networks, because they can broker information. They have access from information of one side of the graph and also the other side of the graph. They can exploit this information that other people might not have access to, for instance. Another way to define centrality would be by using some tools like PageRank. So PageRank is, well, what Google used to use 15 years ago to rank pages on the web. And how did they do? Well, they defined a centrality measure for directed graphs. And this centrality measure was defined in a recursive way. And it was said, so a page would be important if it receives many connections from important pages. So it seems to be a definition that is like a circular, but actually yes. And if you're important if you connect if you receive connections from many important pages, each of them being important if they receive many connections from important pages, and so on and so forth. And you can show that actually if you write this expression mathematically, in terms of matrices, everything reduces to a simple eigenvalue problem. So you will have that the PageRank, the importance of a node, relates to a certain eigenvector of a certain matrix. So it's way to say that linear algebra can be important. And you can become rich with linear algebra too. So that would be cohesion, centrality. Another kind of something extending a bit on triangles would be looking at other kinds of local configurations. And that's something that people are very much interested in, for instance, in biology. So in biology, there are many biological systems where they can be represented by networks. And in biology, people try to find some building blocks by which the system has evolved in time. And typically, these building blocks might be certain types of connectivity patterns that you observe at a very high frequency, much more than you would expect by chance. And here, for instance, that would be a situation where you look for certain types of motifs in a graph, and you try to estimate whether or not this number of motifs is high or not. K-core and core periphery, so what would that be? So, well, this one I will not mention. And so degree-degree correlation, so that's something that also people have been quite interested in is, so when you have an edge between two nodes, you can ask the question, do I tend to observe that high-degree nodes are connected to high-degree nodes more than I would expect by chance? Or do I have that high-degree nodes are connected to low-degree nodes? And this can lead to very important differences for how the system is behaving, but also in order to understand how the system has been constructed. Because if you have a high propensity for high-degree nodes to be connected with each other, well, you can think that if you imagine the system, you will have a very dense core with high-degree nodes connected with each other, and then the outer ring, where you would have weaker nodes with a small degree that are less connected to this core than the other ones, and that would also lead to very different types of functioning for these systems. And the last point that is a bit related to this one, and that's something that is extremely important in practice, is there are many situations where you can have some metadata about a network. For instance, you have attributes about nodes. So you know that each node in a social network has a certain age, has a certain gender, might have a certain taste in music, might have whatever. So you can characterize nodes by some data. And then what you can try to understand is do I tend to observe that neighboring nodes share the same attributes? So statistically, do I have that nodes with the same attributes are connected with each other? And for that, there are some simple measures of homophily that simply try to estimate whether or not around an edge you tend to observe that the same attributes are present or very different attributes. And again, for instance, in social networks, there could be, well, it's something that has fascinated social scientists for many years to understand. Let's assume that you have homophily. Let's assume that around an edge you have the same kind of attributes. Well, is it due to the fact that people with the same attributes tend to connect with each other? Or is it due to the fact that once you have a graph, the attribute is diffusing and the taste of the people is evolving? Well, it depends. I suppose if you think in terms of the color of the eyes, that would be the first answer. For the color of the eyes, well, usually it doesn't change too much. And so for that, if you have an homophily for the color of the eyes, it might be that people with the same eye colors tend to connect with each other. But if it's about the taste of music, it could be both ways. I could make friends with someone because he likes the same music as I do, and we went to the same concert. Or I could be friends with someone, and I could try to push him to listen to certain types of music because my taste is the best. And you see that when you have homophily, well, of course, as with many systems, it's very different to know if what you observe is a correlation or a causal relation. But at least you know that there is something. You know that certain types of attributes tend to be correlated with each other around edges. And for that, there are these measures associated to what's called homophily in order to deal with that. What time is it? So it's 10:34. Maybe if it's fine for you, could just have the small break now. Is it possible? Because basically, so during the first hour, so I've been discussing more like generally about the different concepts. Now, during the next hour, so I'm going to focus on something very particular. That's something called community detection, graph clustering. Well, what we try to do is to consider a graph, and we try to find groups of nodes that are densely connected with each other. So it's really a clustering problem. And what I was planning to do during the next hour is to talk about one type of method that is very popular now, to show you just a bit in detail how they work, and also to show you some limitations that it has. But that would be for the second hour, if it's fine for you. Okay, thank you. Many networks tend to be modular. So networks are not So we've seen that they are heterogeneous in the sense that the degrees are heterogeneously distributed. But besides that, they are not like one set of nodes all connected in a relatively slim way with each other. They tend to be made of groups such that most of the connections are within the groups, and there would be few connections between nodes of different groups. So that's something that can be observed. So I think that I'm going to skip that. So that's something that can be observed in many systems, and where schematically that would look like something like that. Of course, here that's an example where things are extremely visible. So like there is a very strong modular structure that we have in an example like this one. And the thing that in practice it will be much more noisy. And one important question is, how do you characterize such a modular structure, and how do you find the groups, how do you find the modules when you're confronted to a network, especially when the network is large? So in practice, what would be this question of community detection? So the idea is that you take as an input a graph, and as an output, what you would like to have is a method that tells you how many groups you have and which nodes belong to which group. So you start from here, and you would be able to say that you have a group of blue nodes and a group of red nodes. And well, that would be a tool that you can use on any graph of that you wish. Now, so community detection is really like a topic that has gained a lot of attention for the last 15 years. So, and there are quite a few reasons why that's kind of tool that is interesting, besides the intellectual questions that are associated to it. The first one is that very often, very often the detection of communities helps you to navigate information. So what I mean here is that, so very often when you have a graph, so personally when I'm confronted to a graph, I just like to draw it, just because I like the idea of visualizing it and trying to get, at least to gain some intuition from the visualization. And that's something that works extremely well on very small networks. But as soon as the graph becomes too large, if you try to visualize it with even the most fancy algorithms for network visualization, well, you will just observe like a group of points that are connected in a fairly in a way that looks completely random, and you would gain absolutely no information from the visualization. So it means that typically when you have a network that becomes too dense and or too large, well, network visualization becomes completely hopeless. So now, why would community detection possibly bring an answer here? Because if you start from a node, if you're able to find the groups of the nodes, then you can change your level of abstraction. And instead of representing all of the nodes, you could simply represent the groups of the nodes. It would lead to a decrease of the size of the system. And you could then try to visualize the network of communities instead of visualizing the networks of nodes. And that's something that actually people like made in practice. So there are some tools now. So that's a tool here developed by some colleagues in Sweden, where they collected all of the Wikipedia graph. So you would have entries for pages, nodes are the pages, and the hyperlinks between the pages would be the connections. And what they did, they built a tool, interactive tool, where you can navigate the Wikipedia system by using this notion of communities and by allowing you to zoom in and to zoom out at different resolutions. So how does that work here? So you would have that each node here corresponds to a community, and in that community you would have thousands of pages, but you just represent the important ones. And the important ones would be then those with the high centrality, as I discussed before. And here the most central one would be big data, for instance. And you see that this cluster is connected to a certain number of smaller clusters. And then in practice, how does it work? Well, you can either zoom out and try to look for larger communities such that this community belongs to a larger community, or you can zoom in and look at the details inside this community. And when you think about it, it's a bit the way Google Maps is working. So if you use Google Maps, well, if you type London, you will see the important streets of London. You will see the important skeleton of London. And it's only by zooming in that you will have the smaller roads appearing, right? So you try to hide the unnecessary details only to show what's important. Well, here it's a bit of the same philosophy. If you're interested in visualizing a very large network, it doesn't make sense to visualize everything. So what you try to do is to try to find a certain level of resolution. You find the groups, you find the connection between the group, and you represent that. And then you let the user decide whether or not if it's the right resolution for him. And then you can zoom in in certain regions, and more details are going to appear in. And so that's sort of a way where you try to play with resolutions, where each level of resolution would correspond to a certain notion of cluster, basically. So that would be one type of application. So another type of application of why to look for networks is the fact that very often when you have clusters, groups of nodes that are present in a graph, they are associated to a certain homogeneity of behavior. So if you think about, I don't know, like web pages, if you find clusters of web pages, it's very likely that these web pages have something in common, either in terms of topic, or in terms of country, or in terms of users that are using them. So it means that if you don't have access to the information about the pages, or if you just have a partial information, you have some data about 2% of all of the pages of the web, but you have the clusters. Well, you can use the clusters as a way to guide you in predicting what would be the topic of a certain page, for instance. Because usually this metadata is aligned very much with the presence of clusters in the network that you're considering. And here it was just an example where, so I think it was an example from Facebook, where we had different types of patterns of associativity in different regions of Facebook. So here you would have a region where I think men and women were connected in a fairly similar fashion, while you would have very, here it would be disassociative. So here we would have that men and women are connected in the same way with each other, while you would have regions where it's not the case. You will have that only men are connected with each other and men are connected with each other. So there are very different regions with very different behaviors that might correspond to different social norms, for instance. And then for the little story, to motivate students especially, so there is something that exists called the karate trophy. So it started as a joke, but it became something extremely prestigious in the field. So, so the thing that when people test community detection methods, the most simple network where people test it is something called the Karate Club. It's a small social network. Actually, I showed it before. So it's this one here. It was maybe the first one I showed, actually. It was this graph here. And you see that I used two different colors because actually it was the outcome of a community detection was to say that there were these ones and those ones. This Karate Club, so it's a network from the 70s by someone called Zachary, who's the name of the scientist. He went to a karate club, and during his stay there was a crisis in the club that led to the split of the club into two groups, basically. And the thing is that this graph is very often used as a way to test an algorithm. It's simple, it's small, it's very easy to find the solution. So it's like the first example where people try methods, typically. And well, because of that, there's been this creation of the Karate Trophy, where if you're at a conference and you talk about the Karate Club, you're the first one to do it at a conference, and the person who has the trophy is in the room, you receive the trophy. And the trophy then goes from group to group around the world. It's been crossing the Atlantic quite a few times. I think it's back in the US now, it's in Colorado. And I've never had it, but obviously I wish to have it. But so please, yeah, you can have it, but after me, if it's fine, yes? Okay, so there is this. So now, what would be a good community? So there are many ways by which you can define communities. Many, many ways. But at least there would be a consensus to say that if you have a system composed of many disconnected components, well, at least as a first order, these disconnected components could be understood as communities, yes. It makes sense to say that two nodes belonging to different components shouldn't be in the same community. And so just for the little story, so the thing is that this notion of connected components is something that has a long history, even in the study of networks and graphs. And it's associated to a certain notion called percolation. So I don't know if you ever heard of percolation, but the idea is the following. So if you took this Erdős-Rényi graph that I mentioned before, if you p equal to 0, it means that for each pair of nodes, the probability is 0 to have a link. Well, the graph will always be like that. If you put p equal to 1, every time you have a pair of nodes, there is a link, you will have a full graph. And the question could be, well, what would you find in between? And if you look at what's happening in between, well, you see that it will not be something continuous. You will have different regimes that appear. And so if you look at the size of the largest component in the graph with respect to the probability or equivalent to the average degree that you have in your graph, these two things are equivalent, what you observe is that when p is too small, the size of the largest component is extremely small as compared to the total size. And at some point, you have a change of behavior, and you have the appearance of a gigantic component. And this transition here is called the percolation transition. It's a phase transition where you go from a regime where you would have many very small clusters to one where you would have one big cluster and a few small ones on the side. And this is something that is extremely well studied. But the thing is that it's just important to keep in mind that for most empirical systems, typically for reasonable data, you will not be with everyone in the same cluster. You will be in a situation like this one. You would have a very large cluster and a few small ones. So it means that if you do community detection in practice, well, you will only consider the largest cluster and try to look for communities inside the larger cluster. And you will assume that all of the small ones there would be independent communities that don't really need very fancy algorithms to look for communities in, basically. So it means that from now on, we will assume that the graph is connected. And what we'll try to do is to look inside this connected component for something finer, some finer structure. So the thing is that community detection, so it's something that emerged 20 years ago, 15, 20 years ago. And it's very related to a very classical problem in graphs and in graph analysis, which is called graph partitioning. So in graph partitioning, it's a problem where you have a graph, and you want to divide it in some homogeneous regions. And how the problem is phrased usually is that you will try to divide the graph into groups by fixing the number of groups and the size of each group. And it's a kind of tool that people use a lot in electronics in order to organize better a board and to have as few connections as possible between different parts of an electronic board, for instance. And the thing is that for community detection, it's a bit different because you don't want to impose a certain number of groups. You don't want to impose the size of the groups. What you would like to have is a method that finds it by itself. So the thing is that in each of those two cases, well, even if the problems, so that you'll see a bit later, the problems look a bit the same, they are different, but they always proceed in the same way. First, what we'll try to do is to formalize the problem. We'll try to define what is a good community. We'll try to give a definition for what would be a good community. And then as a second step, we'll try to find a way to search for it. And these two steps are not trivial. Like defining what is a good community, it's a very highly debatable problem. But even if you've defined a good definition, then searching for the good communities, given the definition, is typically a very hard, computationally hard problem, and you need some fancy and some smart methods in order to find them or approximations of them if the graph is too large. So I just wanted to mention that, so today I will only focus on certain types of methods where we will assume that each node belongs to one single group. So it means that each node will belong to one community, not zero, not two, just one. So what we'll do is we're going to partition the graph into different regions. And in certain applications, it's a very fair approximation. But but in other situations, it could lead to very paradoxical or unreasonable outcomes. And so, for instance, if you're interested in social networks and you're interested in small groups in social networks, well, that wouldn't be a good approximation because as an individual, I belong to several groups. I would have my groups of colleagues. I would have groups of my family, my group of friends, and typically these different groups are not connected with each other. And so it means that I, as an individual, I don't belong to one single group. I belong to several groups. And so it means that, for instance, for social networks, if you're interested in groups or communities, social groups around people, then you should look for methods allowing for overlapping communities. But that's not what I'm going to deal with today. So, but there are some methods for that as well. So here I'm going to focus on situations where each node belongs to one single group. So, okay, so now what about, so as I said, so community detection is somehow related to the graph partitioning problem. Now, for the graph partitioning problem, typically what you would do, so as I said, you would have a graph, and a very simple scenario would be you say, I want to divide my network into two groups, one with a certain size N1, the other one with a certain size N2. And that's my problem. And how do I say that the partitioning is good? One way to say so would be to say that I want to find a partitioning such that the cut size is minimal. So what would be the cut size? You have a group of nodes here, a group of nodes there. The cut size is the number of links between the two groups. And what you say is that you want the cut size to be as small as possible. So you want to arrange the groups and to put some nodes on the left, others to the right, such that you will have as few connections as possible between the two groups. And that would be minimizing the cut size. So, of course, that's a node. So we have the definition. We define the problem. Now you have to, if you want to solve it, you need to find the best partition. It becomes an optimization problem. And well, the very naive way would be to look for around all of the possible partitions and to pick the one with the best value of the cut size. But of course, it's completely infeasible in practice because the total number of bi-partitions is something in a graph grows much faster than the exponential. So it means that you cannot do it in an exhaustive way. So you need to find some heuristics. You need to find some ways to find for a good solution in a smarter way than that. And there are quite a few methods that have been proposed in the literature, one of which exploiting the matrix structure of a graph. So the algebraic, so the linear algebra associated to a graph structure. And so these methods are called spectral methods because they are based on the spectral properties of a certain matrix of the graph. So here maybe I wish I have more time, but maybe I'll just go a bit fast, but I can give you some references if you want. So basically what you do is you say that what is the cut size, R, so it's 1 divided by 2 of a sum of all pairs of nodes that are in different groups. So I don't take pairs of nodes in the same group, they need to be in different groups. And I sum Aij. And if you remember, Aij was equal to 1 if there was a link, 0 otherwise. And so I divide by 2 because, of course, if there is a link between I and j, there is another one between j and I. So I count the same link twice. So I need to divide by 2 here. Yes. Now, the thing is that this expression, it can be rewritten very easily by using a certain indicator vector Si. So Si would be something that tells you that node I belongs to the community +1 or to the community -1. And if you encode the belonging of the assignment of the node to a certain community with this vector, well, you can in just a few lines you can re-express R in terms of this expression here. While L is a new matrix. It's a matrix called the Laplacian of the graph. And what you would have is that you have 1/4 of a sum of all pairs of nodes this time, without this constraint anymore, of this matrix, the Laplacian, times Si times Sj. And so it means that optimizing this or that is just the same, yes? And now if you want to optimize this quantity, one way to do so would be to think of a relaxed problem as compared to the problem that you have originally. So originally what you would like to find is to find the best vector S, having made of +1s and -1s, such that this quantity is as small as possible. It's a difficult problem. What is a much easier problem is to say I want to find a vector S without this constraint that minimizes this quantity here. And if you do so, well, what you will have is that, so Lij is a symmetric matrix. you know that because it's a symmetric matrix, its eigenvectors are going to form a base of the space. The Laplacian has very nice properties. It can be shown that its smallest eigenvalue is 0, and all of the other ones are positive. And if you keep all of this information together, you plug everything together. So Lij is a sum from 2 to n, because the first one is 0, of the eigenvectors times the product of the eigenvalue times the product of the eigenvectors. And if we put everything together, you will directly see that what is the best value vector S, the one that minimizes R, that would be a vector that is parallel to the eigenvector of the smallest eigenvalue. Why? Because you would have that if it's parallel to the vector with the smallest eigenvalue, only the lambda 2 is going to appear. All of the larger ones will not appear. And so you will only have contributions from the modes with the smallest eigenvalue, lambda 2. And so it means that if you want to minimize this quantity for the matrix L without constraints, well, you would have that actually you need to take S to be proportional to the eigenvector with the smallest eigenvalue of that matrix. And you can then even say that the cut in that case will simply be equal to, is going to be proportional to the corresponding eigenvalue. Okay, so I hope it roughly makes sense. So now, of course, so it means that here we can solve the problem very easily for general vectors S. But how do we do in practice? Because we want to cluster the graph. But then in practice, what we do is we find this eigenvector, and we try to find a vector with plus ones and minus ones that is as close as possible to the eigenvector that we found. So for instance, let's assume that this would be the eigenvector. So that would be all of the entries of my eigenvector. I will reorder them from the largest one to the smallest one. And what I will do is, let's assume that I want to find a grouping into two groups, one of size 4, the other one of size 15. What I will do is I will put together the 4 nodes with the highest values, and I will put together all of the nodes with the 15 lowest values. I will try the opposite. I will try to put together all of the nodes with the 15 highest values and together the ones with the 4 smallest values. I have 2 candidate partitions. And for each of those 2, I calculate the cut size, and I pick the one that is best, basically. And well, there is no board around, no. But really the idea is that, so if you think of this, you would have like a vector, you will have something that decreases. And what you try to find is the best step function made of ones and minus ones, the step function that is as close as possible from this that is not a step function. So really the optimization that we do is we first do the optimization, the easy optimization for any vector, and then we try to find a vector that satisfies the constraints that is as close as possible from the exact solution to the approximate problem. That's really the way it works. Good. Now, why do I talk about that? So that would be for graph partitioning. It's a classical problem, and these tools of these spectral methods, they were defined, well, they originated by works of Fiedler in the 1970s. Now, the thing is that it's going to appear in a very similar way for community detection. So in community detection, as I said, now what we have is we'll build a quantity that tells us if this partition is better than this one or that one or that one. So it would be a quantity that tells you what is the best partition, whichever is number of clusters and the size of the clusters. Yes?
Sorry, I was just wondering if this method can be extended to clustering of more than 2 groups.
Yes, and so yes, of course. So the thing that typically then it's used in a recursive way. So you would find the best bipartition, and then you will continue to cluster it down by clustering the groups, and you continue until, well, and then each level you look if you have a better partitioning than before, or like a better cut size than before. So now the thing that for community detection, so there is also something equivalent to cut size that people use. So but actually there is not one single answer, and I'm going to try to emphasize that at the end of the talk. So, but possibly the most popular quantity to estimate the quality of the partition of a graph is something called Neumann-Govan modularity. It was defined in around 2004, 2005 by Mark Newman and Michel Govan. And as you'll see, it's not perfect, but many people use it, and it works relatively well. So what would be the definition of Neumann-Govan modularity? So you take a graph, you take a partition of a graph, and you try to characterize the quality of that partition. And you would have that the Q, this Q for modularity, would be the fraction of edges that you have and that are inside the communities, and you subtract the expected fraction of edges if everything was to be random. So you see that null models appear one more time. So now, in practice, how would you do that? Well, you'd have that modularity. It's just a constant, which is not very important here. You have a sum of all pairs of nodes. And these sums are such that you only keep terms where the nodes I and node j are in the same community, such as Ci is equal to Cj. They are in the same communities. And then you have a positive and a negative term. So the positive term counts the edges, simply. Aij counts the edges between I and j, such that I and j are in the same communities. But then you subtract something else. You subtract Pij, and Pij would be the expected number of edges between I and j in something that is random. And the thing is that very often what is used here to estimate the expected number of edges between nodes I and j would be the expectation for the configuration model, the one I defined before, where you would assume that you have a completely random graph except for the degrees of each node. And if you remember, I told you that the expected number of edges between a node I and a node j for the configuration model would be this quantity here. It would be proportional to the degree of I and the degree of j. So basically what do we do here? So we have a positive and negative terms, and it really takes this expression here, and we say that the modularity is high if it tends to group nodes together such that the difference here is very positive. And the difference here is very positive in which situations? Well, when you have edges between nodes that wouldn't have that are less likely to be connected than they would be by chance, basically. And this quantity here, so it's called this Neumann-Govan modularity, and that's what people use as an objective to optimize in order to find the best partitions of a graph. So there are many things that can be shown about modularity. Well, the first one being that the modularity of one big cluster, where you put everyone together, is going to be equal to 0. So I didn't say that. So modularity, it's a number that by definition is between minus 1/2 and 1. You know that if you have 0, you put everyone together. And what can also be shown, well, so it's a bit of math, but you can show, and it's relatively intuitive, that if you have a community, if in your partitioning you have a community made of nodes in different connected components, you should divide that community because it's going to be better. So it makes sense. You will never have, by optimizing modularity, groups of nodes that are in different connected components. So it seems to be relatively intuitive. Now the problem is, one first problem is that it was shown that optimization of modularity is NP-complete. So you need heuristics in order to be able to give some approximate solutions to the optimization problem. And what I'm going to talk about now is two ways by which you may try to optimize modularity. One that inherits, basically it really builds on the spectral methods for graph partitioning. It's going to be a spectral method. And then another one, which is a greedy method, and that has very different nature, as you'll see, and each type of method has its own advantages, basically. So what about spectral methods? So here, actually, it can really be done. It's almost a translation of what we did before. So here you would have that instead of trying to minimize the cuts, what you try to do is to optimize modularity. And this modularity, if you look at it, you have a matrix that is Aij minus Ki Kj divided by 2m. So that would be the matrix that you try to that is used in the summation of your modularity expression. And typically for using spectral methods, the way it works, and it relates to your question, is you first try to find the best partition into two communities, and then you redivide the communities, each one of them, and then you continue to do it from the top to the bottom. And then basically at each time you divide, you check if the modularity that you have is better than before. And at some point you stop when you get the best level, when you get the best partition that has been obtained always by dividing by 2 and by 2 and by 2 and by 2, from very big communities to very small communities. And at each subdivision, what do? Well, you have your matrix. You can again, for the division into two communities, use the same vector as before, +1, -1. And then you would have that the modularity Q is obtained by this expression here. And again, you solve the approximate relaxed problem where you don't impose S to be +2 or -1. You impose S to be, you don't put a constraint on S. You ask what is the best S that maximizes Q. Well, before we wanted to minimize the cut. So for the minimization of the cut, we had to look for the eigenvectors with the smallest eigenvalue. Here for the maximization of modularity, we'll have to find the S with the largest eigenvalue, the one that leads to the largest contribution to the sum. And basically, the spectral method tells you that you will take the vector, a vector S, that is the dominant eigenvector of your matrix, the one with the largest eigenvalue. And how do you go back to the original problem? Well, that vector might have positive entries and negative entries. You don't have any constraint. You want to put a Heaviside function on that, but you don't want to impose the size of it. You just want to have +1s and -1s, but you don't know exactly the size of each of these. Well, what you say is that I will put as a +1 all of the positive entries and a -1 all of the negative ones. Yeah? And so you would really look, you rank all of your entries in a decreasing fashion, and all of the positive ones you put on one side, all of the negative ones you put on the other side. And that would be the outcome of the optimization for the first bipartition. And once you do it, you continue on the smaller ones, and you apply recursively, basically. Now, so that method, it's a method that worked relatively well. So it's been refined quite a bit since it was first presented, but the ingredients remain the same. And this kind of method, it works quite well. It has a nice mathematical nature. But it has one limitation, is that in order to do it, you need to solve large eigenvector problems. And typically, if you have a graph made of millions of nodes, it will not be tractable. So typically, it works well until tens of thousands of nodes, roughly speaking. After that, it doesn't really work well. It doesn't scale well with the size of the system. So for networks that are larger than that, well, then people use completely different methods that are greedy methods, where instead of proceeding in a divisive way, using spectral arguments, they build in an agglomerative way. So they try to build clusters from the small to the large, using some greedy approximations. And so basically, so there are different methods that are using such greedy ingredients in the literature. I will be just a bit self-referential, and I'm going to present the one I was involved in, partly because I know it well, first of all, but also because, well, we were lucky that it's the one that everybody uses. So it was the winner-takes-all one. And so that's the one that is implemented in most of the libraries nowadays. So how does that method work? So it's called the Louvain method, because at the time I was in Louvain, in Belgium. So how does it work? So what you say is that you start from your graph, and initially you put a random order to all of the nodes. So this is node 0, 1, 2, 3, 4, 5, and so on. And then what you do is the following. And initially you say that each node belongs to its own community. So node 0 belongs to its own community, 1 or so, 2 or so, 3 or so, and so on. And then what you do is the following. You start from node 0. You take it out of its community. And you check if there would be a gain of modularity by putting it into the modularity of one of its neighbors. And you do that for all of the neighbors. If there is no gain, node 0 remains where it is. If there is a gain, if changing it from community from its own to another one leads to a gain, you do the move that that leads to the highest gain. So you move to the community of your neighbor that leads to the highest increase of modularity. You do that for node 0, for node 1, for node 2, for node 3. You do it sequentially until node n-1. And n-1, you go back to 0, and you do it several times. And every time you do a very greedy local optimization. You always change the community from one node to one of the neighboring ones. And you do that until you reach a local maximum. You cannot increase modularity anymore. And you reach a plateau. You get a local maximum. You cannot move. Once you get there, you do something else. Once you get there, you somehow change the resolution at which you look at the problem. And that's why it's some sort of a multi-scale method, because you will see that you will change the way you do your greedy steps. First, you do it between neighbors. Then you will do it between neighboring communities. So how do we do? So once you get the local maximum, we change the representation. And from here, we go to a representation where you would have nodes being communities and connections with weights being the number of links between the communities. So for instance, between the green and the blue community, you see that there are 1, 2, 3, 4 edges. We don't want to lose that information. And we want to have something, a representation where both of these things are equivalent to each other. And so basically here we also have a 4 that tells us that there are 4 links between these two communities. And what do we do now? So we change the resolution. By doing that, we decrease the size quite drastically. And then the next step is we reapply the first step. So it means that on this one, we again say that we try to say this one is in its own community, this one as well, this one as well, this one as well. And we try to move it into the communities of the neighbors until we get a maximum. And then we change the resolution again, and we do it always the first step, the second step, the first step, the second step, until we get a situation like this one here, where nothing evolves anymore. And so really, so it's a method where, so it's very greedy, because we only do things for the best choice always. It's very local. We always move to the neighboring nodes. But it is slightly multi-scale, because it looks at things locally initially between neighboring nodes. Then when you are at this representation, it looks at things between neighboring communities. So you allow groups of nodes to move together. And the more steps you do, the larger groups of nodes you try to move around the graph, basically. And the thing is that, so it's a method that works quite well. And so here's just a visualization. So we start from here. We get the local maximum. We change the representation. We have another local maximum. We change the representation, and nothing happens anymore. And that's where it stops. Yes?
How sensitive is this to the initial random allocation?
Well, it's a very good question. So it's a method that is deterministic. Besides, well, two possibilities. One would be, I said that I would move to the community of the neighbor where the increase is maximum. But if there is a draw, we pick one at random. So that would be one aspect of noise. But the most important one is the fact that we see here that the algorithm depends on the ordering in principle, which is the first node that we use. And we set it as something random here. And the thing is that, well, in practice, what we observed was that the order doesn't have too much of an influence if the network has strong communities, as well-defined communities, while if you have a system where the communities are extremely noisy, then you might have very different results at the end. And actually, it's something that we use somehow as a verification, is we use the method 10, 20 times on the same graph with different orders. And if we always get the same communities, it means that the method is robust, and it's quite likely that the results that we have are to be trusted. While if we get very different results, it's kind of likely that then the communities are very weak, and you should look at them with a lot of care, basically. So as I said, and that's a method that is really different in philosophy as compared to the previous one, because the first one was divisive, this one is agglomerative. And now in practice, it's good for certain aspects, is that it's very fast. And so that's a table from the paper from almost 10 years ago now, where we looked at the time at the fastest methods existing on the market. The Karate Club, as usual, 34 nodes, 77 edges. And the largest that we considered was a part of the world with 100 million nodes and 1 billion edges. And for each one, we reported the value of modularity that we obtained from the optimization and the time that it took on a standard desktop. I think it had maybe 16 gigabytes of RAM because we needed to store the graph. But besides that, it was a standard computer. And we observed that, well, that was convinced, I guess, the community that we always had a much higher value of modularity as compared to the existing ones, and that the times were also relatively fast. So like for this one, it took about 2 hours to do the optimization. So now, what time do I have? It's okay. So now, so generally, so something that is important to keep in mind is generally, so I just presented to you 2 methods, each one based on the notion of modularity. So now the question is, of course, there are not the only 2 methods. There are thousands of methods nowadays for community detection, a subset of which looks at modularity optimization. And the question would be, well, how do you say that one method is better than another one? Well, of course, first, if you're interested if you first want to compare methods that try to optimize modularity, well, you can just first compare the value of modularity that you have. And the highest is the better, because it's an optimization problem. You have a heuristic. So you try to find the method that gets you the best values, ideally in the fastest time. So there's a balance usually between accuracy and the speed of the method. But that's of course something that you can only do if you want to compare methods that are both trying to optimize modularity. If you take a method that optimizes modularity and a method that optimizes something else, that would be unfair to compare them with modularity, because of course the first one will win because it's what it tries to do. Then for these other types of methods, what some people try to do is to try to check if the communities that are found tend to be aligned with some metadata that you have. So here is an example that is visually striking, but socially extremely expected. So that's a mobile phone network of Belgium. In Belgium, we have 2 languages, French, Dutch, and a bit of German too. So I should not forget them, also because it's recorded. So mainly we have 2 languages. And here you have the communities that are found by the methods. And where basically what you have is that each blob here is a city. And you have that most of the cities with a certain language are communicating with each other versus other cities. And there's just a tiny part here that is a subset of Brussels, the center of Brussels, where Flemish and French-speaking people live in peace together and talk with each other. And basically, of course, that's something that you don't need very fancy methods to know that, but you can show it from the data. And so the one way to test a method would be to say, well, actually, I find communities, and these communities tend to be homogeneous for certain data, for some data that I have about the nodes. But you cannot be sure that structural communities are aligned with this extra information. So it's not clear that that would be the best way to do. Another way that people used as well was to build some benchmarks. In these benchmarks, what do they do? So you consider a variation around the Ardashani model. So it's a random graph. But instead of having that, so for Ardashani, remember you have for each pair of nodes a certain P to have a connection. What you do here is you assume instead that you have something called a stochastic block model. A stochastic block model means that the simplest one would be you take 2 groups of nodes, and you have a priority P1 to have connections inside the first group, P2 to have a connection inside the second group, and P12 to have a connection between nodes of different groups. And typically, if P12 is smaller than the other 2, it means that most of the connections are inside the groups, and you have fewer connections between the different groups. Yeah. So basically, it's a random model where you plant communities, and you have some noise, and you have potential connections between the nodes. And then typically what you try to do is you try to see if the communities that you find by your method are those that you planted initially, basically. And what you try to do is you compare the quality of your answer as a function of how difficult it is to find a solution, And how difficult it is typically, well, does the P12, is it very, very small, or is it of the same order of magnitude that the P's inside the communities? And typically, you get something where most of the methods are good initially, and then, of course, the quality decreases at some point. And you can say that a method is good if it pushes this border the more to the right, basically. Well, again, that's something that works well, but it also has some problems that there are many, many ways to build benchmarks. And somehow, when you build a benchmark, you build your own intuition of what would be a community according to you. And sometimes you would have that some benchmarks are, well, some methods work extremely well on some benchmarks and others on other benchmarks. And, well, it's not always clear what would be the best either, I guess.
Are there any supervised approaches?
Excuse me?
Are there any supervised approaches?
There are some supervised methods. It exists, yes. So, well, I want to, well, but first of all, it's not really about supervised or unsupervised. But so what I will mention just after is that there are some methods that are model-based approaches, where what you try to do from a statistical perspective is you try to find the best stochastic block model. So you try to find the best structure in blocks and the different probabilities that explain the network that you have. So really what you have in mind is you have some data, you have a model of your data in mind, and you try to find the best parameters that explain what you observe. And that's something where there's been a lot of work for the last few years on that, but it's still unsupervised. For supervised, there are some work where they try to incorporate some partial knowledge of the communities, for instance, and to try to build around that. And some simple ways would be, for instance, to do some seed expansion, for instance. So if you know that 3 nodes have the same community by the information that you have, then typically you do some search around them, and you will assume that in a sufficiently small neighborhood, the nodes will be in the same community, for instance. And so that's another way where you can try to infer what are the communities. Another way to do that is kind of nice is to directly ask to the people. And so there was this experiment by someone who's working for Facebook now, where what he did at the time during his PhD was to develop a method for community detection, like many people, and to say if the clusters that he found were good, he asked users to rate the clusters found in their social network. So it's on Facebook, you log in, it takes your social network, it does a cluster, and then it presents you the clusters, and you need to give stars to different clusters to assess whether or not it makes sense to you. In that case, well, it was a nice experiment. Of course, it's difficult to scale it very much because you need to have the active participation of users. But I think that in that case, it had maybe 500 people who participated, and so used that as a way to validate these methods, because it allowed to give ratings based on the expertise of the persons themselves. So, okay, so I don't have too much time. So especially, well, the idea was to leave maybe 5 minutes for questions, so I have 5 minutes left. So I'll just go through some problems of modularity. I might not say everything. So the first problem of modularity is the fact that in practice, if you do your optimization, you will have that in many, many empirical systems, you will have a very rugged landscape. Meaning that even if you find a very high value of modularity, close to the optimum, you will have that this solution might be extremely different from that one. So this cluster might be very different from that one, even if the value of modularity is roughly the same. And it goes into the discussion that you had about the ordering. Well, it could be very well that for Louvain, for instance, with one random ordering, you arrive here. With another one, you arrive there. You get roughly the same value of modularity, but you have very different answers. That would be a possibility. So that's something that needs to be checked. How robust are your solutions, knowing that the optimization problem is not easy to solve. So another thing that is very annoying is something called resolution limit. And it's the fact that community, so I didn't say too much about it, but modularity, in principle, when you find the best partition, you will have a certain number of communities, and you didn't decide on that. So the method magically decided what was the best number of communities. That's good. But now the problem is that it's quite easy to find examples where this number of communities that you have doesn't make any sense. And one example would be this one here, where you have a circle of cliques that are connected with each other. If you have a small number of cliques, modularity optimization is going to find the cliques. But then if the number of cliques becomes too large, what you will find is groups of cliques. And of course, it's not a very physical or intuitive solution. There is no really meaning why you would put these two together, because, well, that doesn't seem like these two together are a very dense cluster. But it's somehow hidden in the method. There is a reason for that. And the reason is that somehow, in modularity, you compare this term with that term. But of course, the M here, if it's large, this becomes very small. And actually, modularity optimization has a size dependence somehow. The larger is your system, the more positive will be this term, and the more likely you will find big clusters in your system. And it could be that the clusters that you have don't make any sense. And so, roughly, it works well. It finds you a number of clusters, but you should not trust it completely because there are many situations where it doesn't work, and it can be shown so. And well, this one is just a bit less interesting. So now, for the conclusion, so in principle, I'm supposed to give a follow-up to this course. So maybe we'll see next term. And what would be next as compared to what I said before? So one thing that could be next, that could be discussed next term, would be the fact that there are many, many other ways by which you can do community detection. So here, the method that we had was really combinatorial. What we did was we counted the number of links inside clusters or the number of links between clusters, and we try to minimize or optimize that. But actually, there are very different perspectives that can be used. Some of them are based on stochastic block models, a statistical approach where you have a model of your graph, and you try to find the best parameters that explain the graph as you observe it. So you try to find the best model that explains the data as you see them, and that's something where people work a lot right now. Another way would be to use a more dynamical perspective and to try to find groups of nodes that have the same impact on some dynamical process. For instance, if you think that a group of nodes should be a group of nodes that play the same role for the functioning, for the dynamical functioning of your system, well, then there can be some dynamical methods that people use in order to find the groups. And just to show something very intuitive, of course, the clusters affect the dynamics. Because, for instance, here that would be a network with some communities. Here that would be the outcome. So x of t would be, so we have, for each node, we have a certain value. And we apply a very, very simple dynamical rule. It's called a local averaging. So it's a consensus dynamics. So you have your value, and you do the average between you and your neighbors. And then each step you do that. Of course, at the end, everybody converges to the average because the averaging becomes global. But what you observe is that at certain times, you will have that inside the different groups, you will have distinct averages. And you can really see that there's a big difference between where you have a separation here between what's happening in the first cluster versus the second cluster versus the third cluster. So typically, you will have consensus taking place initially inside each of the groups, and then you go to the global consensus. And this is something that can be used in order to find the clusters in empirical data, for instance. Another thing that is quite interesting is so far we only focused on structures like those. We tried to look for clusters so that the links were inside the clusters. But there are other types of patterns that could be looked for and that can be very important in different systems. For instance, you could have something like a core periphery type of organization where you have a core. The core is connected to the periphery, but the periphery is not connected to the periphery. And that's some type of organization that can be present in certain systems. Another one would be some bipartite type of organization, but what you can have in mind is not only looking at things around the diagonal, but other kinds of patterns that reveal certain types of organization that are present in the system. And I think that I'm going to stop now. So I just have a few references for you. So for general references, a very good book is the one of Mark Newman. It's really very elementary, and it goes into some of the details. It's quite good. I couldn't not put a book that I wrote, but I don't. If you want to read it, I will not say too loud, but send me an email. I'll send it by PDF because it's extremely expensive. So I don't think it's. Yeah, I think for free it's a good thing to read. For 100 pounds, maybe not. So don't hesitate to send me an email for the PDF. We talked a bit about power laws. For power laws, there's this very nice review from 10 years ago about why you would accept to find power laws in heterogeneity in systems in general. And then there's this nice paper there that proposes method to test whether or not you have power laws in empirical data. These two ones are very nice to read. And about community detection, so there's a very old paper that I advise by Herbert Simon called The Architecture of Complexity. It's just a pleasure to read. There is no math. It's just a story. And it tries to explain why you would expect things to be modular and clustered all around the world in nature and in society. There is this review paper by Santo Fortunato from 2010. There was a recent follow-up last year or 2 years ago, but it's roughly the same about all the different types of methods that exist for community detection. And then there is this other paper here, which is about trying to understand the different types of philosophies that exist in community detection by Michael Shaw, which is a bit shorter, and that could also be of interest for you. And I think now it's time for me to stop, because I will have to leave at 11:45. So it means that I can give 4 minutes for questions if you have any. 3, 4. Let's say 4. So thank you very much. Thank you.